All right, in this video, I'm going to run through the homework on pages 226 and 227, looking at the first derivative test, increasing, decreasing intervals, and local or relative extrema. Here we go. Problem number 3. We have an original function, f of x, x squared minus 6x plus 8. We know that this function is quadratic, and we know that it is an upward opening parabola. We can see that the vertex of the parabola occurs at x equal to 3. We know that the first derivative, there's a horizontal tangent there. We know that 3 would have to be a critical number. But we don't have to use any of the first derivative test to determine the increasing and decreasing intervals, because visually we can see that this quadratic function f of x decreases all the way up to x equal to 3 and increases after 3. We don't have to justify anything for this, so for number 3 they just wanted to know, where does this function increase and decrease? So the function f of x, let's be more specific, f of x decreases on or from negative infinity up to 3, and that's going to be an open interval, not a bracket. And we don't have to justify, we're not using the first derivative, we're simply looking at the original function. F of x increases on the interval from 3 to infinity. That's just visual inspection. All right, looking at number 5, we have the same sort of thing going on. We can see that the original function, in this case y, is increasing up until x equal to negative 2, decreasing from negative 2 to positive 2, which is here, and increasing again after 2. So in number 4, or actually number 5, we would say y is, let's start with increasing on, and that is from negative infinity, and these are x values, up to negative 2, that's an increasing interval, and then the function increases, the function y increases again, starting at 2 to infinity, and again, no justification is needed. We're looking at the original function, and we can see where the function goes up and down. The function y is decreasing on the interval from negative 2 to 2. All right, so just visual inspection. All right, let's go back to the next problem. Let's see, what's the best way? I'll just clear the annotations. That's going to clear my circles as well, but that's okay. All right, number 21. In this section, we are looking for the local maxes, the local minimums, the increasing and decreasing intervals, and we do not have the original function. We do not have the, I want to move these graphs out of my way, actually, just so I have more space. Gone and gone. And I'm going to move those up. And where's my eraser? There it is. Okay. So looking at number 21, we have a cubic function. We do not have a graph of it. We could take a look at it, but we're going to use the first derivative test to determine the increasing, decreasing intervals, as well as any local extrema that we might find. So we need the first derivative, so f prime of x, using the power rule, is going to be 6x squared plus 6x, and the derivative of 12, I better check that to make sure that that was not a miscopy and that there's an x there. So as I suspected, I'm glad I stopped to check that. There is an x here, so that's going to change. So the derivative there is minus 12. I'm going to set the first derivative equal to 0. I'm also going to factor a 6 out of every term, so it's going to be x squared plus x minus 2, set equal to 0, and I'm setting the first derivative equal to 0 to find the critical numbers. I'm going to factor and get x and 2 and 1 and plus and minus equals 0. Now, the 6 we could divide over to the other side and get rid of it. So we're not going to set 6 equal to 0. We're going to set each of these factors equal to 0. And we get x equal to negative 2, x equal to positive 1. And these are my critical numbers. Remember, Critical numbers have potential. There could be local max, local min occurring there. So we are going to create a first derivative number line. This will be the work that I would expect to be seeing on your paper when I collect your mystery work. Make sure you name the number line because there is going to be a second derivative test. So we need to make sure we know which number line we're looking at. So I'm going to put the critical numbers of -2 on the first derivative number line and the critical number of 1 on the first derivative number line. That breaks the number line into 3 regions, and I'm going to choose a value in each region. So for example, in region number 1 to the left of -2, I'm going to choose -3, and I'm substituting. This is why we named the number line. I'm substituting into the first derivative to determine the sign, positive or negative. So if I take a -3 and I substitute a -3, when I substitute, I'm going to substitute into this factor. This is the easiest place to substitute, and to this factor right here. Now the 6 is positive, so I can put that 6 in front if I want to, just to make sure I don't forget about it, because if it were negative, it could have an impact. So I'm substituting a -3 into this to the first factor. If I substitute -3 here, that'll give me a negative. Substitute -3, that'll give me a negative, and a negative times a negative is a positive. So in region 1, the first derivative is positive, meaning, or telling me that the original function increases. Both the plus sign and the increasing arrow are required for my class. I'm going to choose a number between -2 in this region right here, between -2 and 1. I'm going to choose 0 because that's an easy number. And if I substitute 0 into the first factor, I get a positive. Into the second factor, I get a negative. And a positive times a negative is a negative. So in that region, the original function is decreasing. In the third region, which is right here, now this is where I am, I'm going to choose a number larger than 1, like 2. Substitute into the first factor here, that gives me a positive. Substitute into the second factor, that gives me a positive. A positive times a positive is a positive. So the original function is increasing. So what I see in red, that kind of gives me a good idea that the original function is a cubic that looks sort of like that. That's why those arrows are helpful. All right, so now I'm going to make my statements. I'm going to say f increases, and we're increasing from -infinity to -2, and then we're going to be increasing again from 1 to infinity. Now my justification, I'm going to justify based on the first derivative, because f prime of x is greater than 0. Or you could say the first derivative, f prime of x, is positive. F is decreasing on the interval from -2 to 1 because the first derivative is less than 0 or negative in that region. Now I can see that I have a local or relative max here, very evident, and a local min here, or relative minimum, whatever. So I'm going to say f has a local max at x equal -2 and is, I'm not going to actually calculate it. Now watch carefully, the local maximum value is the function value, so it's f original of -2. And now I got to justify why. Because f prime of x equal 0. Actually, let me erase that. I'm going to be more precise. So first of all, I'm going to establish, after my eraser comes in, I'm going to establish a critical number. So I'm going to be very clear. So f prime of -2 is equal to 0. That establishes the critical number, and f prime of x changes from, and you have to be specific, positive to negative at x equal -2. Be specific, be specific. F has a local min or relative min at x equal to 1 and is original function, it's a y value on the original function, f of 1, because f prime of 1 equals 0. Notice how I have to be careful which function I'm referring to. Right now I'm trying to establish a critical number, so I'm going to state that the first derivative is 0. And the first derivative, f prime of x, changes from negative to positive at x equal 1. All right, so be specific, and don't leave out anything. All right, let's clear that, and let's go to the next problem, which is number 25. Now, when I do number 25, I'm going to begin by doing a rewrite with that fraction in the denominator. So I'm going to say in number 25, f of x is equal to 1/5 x to the 5th. I'm going to break the fraction apart, minus, and then where I have right here, I can do 5 over 5. That's just going to be x. So that's just going to make my life easier to find the first derivative. I'm going to find the first derivative to locate my critical numbers. So f prime of x is equal to 5 times 1/5 is 1. So that's x to the 4th power by the power rule, minus 1. I'm going to set the first derivative equal to 0 in order to find the critical numbers. So x to the 4th is equal to positive 1. Take the 4th root of both sides, and x is equal to positive or negative. Don't forget the negative, because that will make a difference in your answer. I'm going to take those critical numbers, and I'm going to test them out. This is the first derivative test. So I'm naming my number line, f prime of x, negative 1, positive 1. All right, so now I'm going to test my critical numbers. And remember, when I'm testing my test numbers, I'm going to substitute into the first derivative. So I'm actually going to substitute into here. So I'm going to choose a number in the first region. I'm going to choose a number to the left of negative 1, like negative 2. And when I take negative 2 to the 4th power, that's a negative in parentheses like that. So that's going to become a positive 16 minus 1 is going to make a positive. So in region 1, the first derivative is positive, meaning the original function increases. In the second region, I'm going to choose a value of 0. That gives me a negative. Original function decreases in that region. And then in the third region, I'm going to choose a number greater than 1, such as positive 2. That's going to give me a positive. So the original function increases. So I can see I have a local max and a local min. So again, with the write-up, I'm going to be very specific. So I'm going to start with the increasing. So f whoops, whoa, slip there. Let's fix that. Right, there you go, eraser. So f increases from negative infinity to negative 1, and increases again from 1 to infinity, because I'm going to justify using the first derivative. F prime of x is greater than 0, or f prime of x is positive. Likewise, f decreases from negative 1 to 1, because f prime of x, first derivative, is less than 0. Now I'm going to state my local max. So f has a local max at x equal negative 1 and is original function f of negative 1. Justification, because the first derivative at negative 1 equals 0, that establishes critical number, and the first derivative itself, x, changes from positive to negative. And then f has a local min at x equal 1 and is original function f of 1. That's establishing the y value on the original function, because the first derivative at 1 equals 0. That gives me the critical number. And f prime of x, the first derivative, changes from negative to positive. And so those are your statements that you use and write up when you're establishing the first derivative test for increasing, decreasing intervals, as well as the local/relative extrema. Okay, that's 25. Let's go to number 27. 27, f of x. So I'm going to go straight to the first derivative because, wait, not 31. We're doing, what number are we doing? 27. I don't know where 31 came from. All right, so this one's already ready. It's ready for me to take the derivative. So f prime of x by the power rule is 1/3 x to the negative 2/3, and the derivative of 1 is 0. I'm going to set the first derivative equal to 0, and I'm going to make that 1/3 times the cube root of x squared set equal to 0. All right, a fraction with a set numerator cannot equal to 0, but there is a place where the first derivative is undefined. So x equal to 0 is a critical number because f prime of x is not defined. So don't forget about critical numbers that we encounter where the first derivative is not defined. So I'm going to take my critical number and I'm going to put it onto my first derivative number line. Make sure you name your number line. And my critical number is 0. So I just have 2 regions to test out. So I'm going to choose a number in the first region. I'm going to choose -1. And I'm going to substitute it into, I think the easiest place to go is here. If I substitute a -1 in place of x and square it, I get a positive. So 1 over a positive is positive, so the original function is increasing. And for the second region, I'm going to choose a +1, which will yield the same result. So I can see that the graph, or the original function, the graph of the original function would be increasing everywhere. And because the original function is increasing everywhere, there are no relative extrema. So the only thing that we can report here is that f of x, or f original, because remember, everything is about the original function. F of x increases on or from the interval -∞ to infinity, because f prime of x, notice, be careful with your names, we're justifying based on the first derivative, because f prime of x is greater than 0, or f prime of x is positive. No local max or min to report, no decreasing intervals to report. And then finally, number 34, I made 34 disappear because I reset the screen. Oh, well, that's okay. I'll just go to my packet and write it down. All right, number 34. All right, here's number 34, even though it's not in my captured problems. 34 is not y equal f of x equal x over x plus 1. Yay, quotient rule. So here we go. We're looking for increasing, decreasing intervals, relative extrema, applying the first derivative test. So we're going to need the first derivative. We're going to use the quotient rule, so I have down, d up, minus up, d down, over, down, down. Let's clean that up. That'll give me x plus 1 minus x over x plus 1 squared. The x's will subtract out, and that gives me 1 over x plus 1 squared. And again, we can see this is another case where we can't make the derivative equal to 0, but there is a value that makes the derivative go undefined. And so at x equal to -1, the first derivative would go undefined, making that making -1 a critical number. So I'm going to put my critical number on my number line. Oh, wow, 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 wow. Very crooked. So let's redo that. I was actually looking at something when I did that. All right, so first derivative test needs a first derivative number line, and it needs a name on it. My critical number goes on the number line, and I have two regions. A number to the left of -1, I'm going to choose -2, and I'm going to substitute it in here. And if I do -2 plus 1, I get -1, but I'm squaring. I mean, really, we can see that the denominator is going to be positive all the time because we're squaring. So that's going to output a positive. Therefore, the original function increases. The number on the right-hand side, since the denominator is always positive, is going to output a positive. So again, we have another situation where the given function is increasing all the time. So I'm going to say f of x is increasing from -infinity to infinity because f prime of x is greater than 0 on its domain. All right, and I think that's all the problems that we had to do in this particular set. So that is the first derivative test.